Hello guys, welcome back to MJ School of Mining and Geology. In today's lesson, we are dealing with interference figures in mineral optics. Don't forget to like, share, comment, and subscribe to our channel. But above all, don't forget to hit the notification button below so that you get notified once we upload new content. So interference figures are nothing but the images which are produced when you have what you call a convergent polarized light, right, between two polarizers, and then also by using high power objective, and you insert Bertrand lens. But sometimes you may not insert the Bertrand lens, and you manipulate what you call the ocular. All right, so nonetheless, which is why we're saying when certain sections of anisotropic minerals are observed under convergent polarized light between two polarizers, and by using high power objective lens and Bertrand lens, an image is produced, and that is what you call the interference figures. So optically, uniaxial and biaxial minerals produce entirely different minerals or different images. So for uniaxial, we call them uniaxial interference figures, and then for the biaxial, we will say they are biaxial interference figures. All right, so these interference figures are used to determine the optical character, that is whether a mineral is uniaxial or biaxial, and to determine the optic sign. So we've already have a video on determination of the optic sign of both uniaxial and biaxial mineral, and also we know different for anisotropic minerals, we've got those that are uniaxial and we've got those that are biaxial. If you haven't yet visited the video, you are more than welcome to visit that video under our YouTube channel, MJ School of Mining and Geology. You'll find these uniaxial and biaxial minerals. So for you to determine whether a mineral is uniaxial or biaxial, you also need the usage of the interference figures. All right, so which is why, and we say, if the mineral happens to be a biaxial class, interference figures may be used to measure the 2V angle, and it can also be used to confirm certain mineral orientation. We have also talked about this 2V angle under the biaxial minerals. All right, so nonetheless, we have what you call, for you to understand the interference figures, you need to understand what you call melotopes, you need to understand isochromes and isojays. All right, so the interference figures is formed near the top surface of the objective lens and consists of a pattern of interference colors called isochromes. All right, so I'll show you with figures what are we really talking about, and then we also have a dark cross, which we call them isojays. Now, the nature of the interference figures and its behavior as the stage is rotated depends on the optic orientation of the mineral grain belonging either to uniaxial or biaxial class. So for you to observe interference figures, you need to focus on a single mineral grain with high power objective lens, and then you need what you call auxiliary condensing lens that must be flipped in. Okay, if needed, refocusing must be carried out, and one needs to open the aperture of a diaphragm. All right, you need to also open the aperture of the diaphragm. Let me quickly show you. You need to open the aperture of the diaphragm, and then you also need these condenser lenses, and you also need these condenser lenses, and then you also obviously need the light source. So you need the light source, you need this diaphragm, and you need these condenser lenses, and of course you need the objectives. Okay, objective lenses. All right, so the upper polarizer is inserted, or the upper nickel, it must be inserted at the upper polarizer. Okay, remember, after from the light source, the first polarizer, you call it bottom polarizer, and it's always inserted. In this case, it's in the north-south direction, and then the upper polarizer, you either insert it or take it out. So if you insert it, we say we are under cross polarized light, and then if you take it out, we are under plane polarized light. If you haven't yet visited our video on plane polarized light and cross polarized light, you are more than welcome to also visit that. So when you now insert the upper polarizer, this will be followed by insertion of Bertrand lens. But like I mentioned before, you may also not insert this Bertrand lens. But now, if you don't insert the Bertrand lens, it means you must remove the ocular, okay, and looking directly down the microscope tube. So it's either if you can insert the Bertrand lens, you must insert the upper polarizer, and also after that you insert the Bertrand lens. But if you don't use the Bertrand lens, you can remove the ocular and then look down directly down the microscope tube. All right. So now we should ask, I'm sure we ask ourselves, what is a melatope? So melatope adjusts the center where the isogers they cross. Is this center, so is this center, and then this is this dark crosses, we call them isogers. So and then it marks the point of emergence of the optic axis. So the optic axis is when we have a sphere, like that, then we have the optic axis, usually coincident with the C crystallographic axis. So then we say this is the OA, the optic axis. All right. And then then light following the optic axis is not split into two rays, and it exceeds the mineral with zero retardation, and hence it looks black. So it looks black. So if I will show you in no time what do we mean when we say the light, okay, the light following the optic axis does not split into two rays, right here. Okay, so this light as it goes up and then past this diaphragm and then into the condensing lens, exactly this one, the metal one, does not split into two rays, and then when it passes through the objective, and then you will see it will form what we call zero retardation. Okay, it will have zero retardation, and then it will look black. Then that's how these melatopes and what you call the isochromes get to come into picture. Then the presence of a single melatope, it means uniaxial, and then two melatopes, it means biaxial. All right. So I hope you understand now. You have you understand what happens to light as it goes up, passing through the diaphragm, and then the light has to be we have to use what we call the auxiliary condenser, and then it making the light to converge. Now can now see that all these lights, they go into the same point. All right, so we say the light is converging. All right, they are coming towards the same point. They are converging. So we need also what you call the auxiliary condenser, but I'm gonna show you in no time. All right, so let's check here. Like already in terms of the isochromes, so we said we need, remember, the light source or the light coming from the bottom, and then after that they would need what you call the auxiliary condenser. And then this auxiliary condenser lens, they make the light to converge, to go to the same point. All right, okay, they converge, this light converge, and then then the light, as it after converging, it will pass through a mineral. All right, it will pass through a mineral, and then after this light will be collected by these objective lenses. So the light, the auxiliary condenser lens, it helps us converge the light, and then this light will pass through the sample, and then after that this light will be collected by the objective lens. But now if you can as you can see here, this light here, So as you can see that this light here, ray path 1, all right, this one, ray path 1. What we notice about ray path 1, it's the fact that this path is parallel to the optic axis. It's parallel to the optic axis. And then if this path is parallel to the optic axis, then you notice that the light does not split. Okay, does not split. And then if it does not split into two rays, and then it will show what you call the zero retardation. And then if it forms zero retardation, you form what you call a melatope. That's what we mentioned when we were talking about the melatope. So that the center of the isogears, which we call it a melatope, it forms by this ray 1, wherein this light does not the light following this path 1 does not split into two rays, and it's parallel to the optic axis, and then by so doing it produces what you call the melatope. All right, I hope you understand. But now let's check the path 2 and 3, for example. All right, so if you can check path 2, it experiences what we call, remember this one, it experiences what you call zero retardation. And then, but now this one, it experiences at least moderate retardation. But now the path 3, it experiences greater retardation, because now if we consider this optic axis, then it means path 1, it's parallel to the optic axis, but now the 2, the angle, it's just not too great, it's moderate. Okay, the angle between optic axis and the path ray 2, and then but now with 3 the angle is greater. So we say path 3, it has got greater retardation, but 2, it has got moderate retardation. But now path 1, because it's parallel to the optic axis, we say it has got zero retardation, and that's where the formation of melatope comes into picture. I hope you understand what we are trying to say. Now then would ask ourselves that what happens if a mineral have what we call high birefringence. Okay, and then if it has high birefringence, it will show what you call more isochromes. So now if you have this picture in mind, let's talk about isochrome formation. Let's talk about a isochrome formation. All right, where are we? Okay, we are here. So like we said, the auxiliary condensing lens provides strongly convergent light that passes through the mineral and is collected by the objective lens you've seen. And then path 1 is parallel to the optic axis, and it will not split into two rays, and it will exhibit a mineral with a zero retardation, and it will form what you call the melatope. And then around the melatopes would have what we call the isochromes. I hope you understand now what we are talking about. Would have what we call the isochromes. All right. And then light, you remember that path 2, it will experience moderate retardation, because it is the angle it's just at a moderate angle away from the optic axis. But path 3, it's at a greater distance, and then it has got what you call the high retardation. So because the optical properties are symmetrical about the optic axis, rings of equal retardation. That's how the isochrome comes into picture. The rings of equal retardation and interference color are formed around the melatope, and that's what we call isochromes. And then the minerals with high birefringence show more isochromes. It means path 3, because of high birefringence, because of high refraction or double refraction, all right, then they will show more isochromes. But path 1, because of it does not, it's parallel to optic axis, it will just show 0 retardation, but now 2 moderate retardation or birefringence. So I hope you understand what we're trying to say. All right, so that's isochrones form by light that split into 2 directions, what you call birefringence or retardation, because they are not parallel to the optic axis. Okay, they are at a certain angle. You can see path 3, 2, 4, and 5. They are at a certain angle away from optic axis. But now, if the light is parallel to the optic axis, we say we produce what you call the Meller tube, because it's what you call 0 retardation. So it does not a double refract, or does not show what you call birefringence. That is the same as in what we call the isotropic minerals. Okay, because the light does not change direction, just go straight. All right, as it passed, or the light from the source, as it passed through that sample, just go straight until it's get to be collected by objective lenses, and then it will show 0 birefringence. All right, and then it's like when then that mineral, it will show color, because it's like we are in isotropic mineral. It will show the same behavior as isotropic minerals. But if now light starts to split into 2 rays, then we say it has got birefringence or retardation. All right, and then now, but retardation, it differs depending on the angle away from the optic axis. If it's just closer to the optic axis, we say it has got moderate birefringence or retardation, but away, we say it has got high birefringence or retardation. Now, last but not least, we have got what we call the isojets. All right, so the isojets, they are simple. Okay, these isojets, they form what we call it's just what you call the dark cross. Okay, and then these are defined as what you call the locus point at which the transmitted rays have 0 amplitude of vibration. They are called dark cross, or what you call the locus point at which the transmitted rays have 0 amplitude of vibration. So what happens is, now when the vibration direction for the light, remember the light will be coming from here, from the source. The light is going up, so the light, it will be emerging from the source, and then goes up. Then here, approximately at the center of this indicatrix, but for this one, it's what you call the uniaxial indicatrix. So now, when it comes from the center of this uniaxial indicatrix, all right, after converging, I can remember we've mentioned the fact that from the source, the light will pass through the diaphragms, and until then it converge at the auxiliary condenser lens. Now, after this, when light converge at this auxiliary condenser lens for what you call a uniaxial indicatrix, then for uniaxial indicatrix, the light emerging from the center, it will show a strong convergent light. All right, and this light, it will pass through a mineral. All right, and then that mineral, it must have the optic axis. It must have the optic axis that is vertical. That mineral, it must have the optic axis that is it's vertical. So let's repeat what we just said. We said the light comes from the light source from the bottom, and goes up, pass through the filters, diaphragms, bottom polarizer, and then this bottom polarizer, it aligns that light in a certain direction, northwest, north-south in this case, and then it will converge in the auxiliary condenser lens. Then now this light, it will now go straight into the mineral. All right, it will now go straight into the mineral. Then when it passes through that mineral, and then what does it do? Then the mineral must have the optic axis that is vertical. All right, so if it has the optic axis that is vertical, all right, you can see here the optic axis is vertical like that. Then the light will be emerging from the center of this uniaxial indicatrix, and then it goes up. And now there are 2 things that will happen. Then now, what happens scoring, the extraordinary rays, they will vibrate parallel. Can you now see? They vibrate parallel. They vibrate parallel to this to this what we call lines of longitude. But now, what about the this ordinary? The ordinary rays, they vibrate parallel to the lines of latitude. They vibrate parallel to the lines of latitude. So these ones, ordinary, they vibrate. All right. So yes. So what happens is the ordinary, they vibrate parallel to the yes, as I was saying, ordinary, they vibrate parallel to the lines of latitude of this indicatrix. Remember, this is the indicatrix, and the light coming from the center of this uniaxial indicatrix, and then where in the mineral have got a vertical optic axis. Then now the ordinary, they are parallel. The ordinary rays, they are parallel to the lines of latitude, but now the extraordinary, they vibrate parallel to the lines of longitude. Now can you now see, remember these lines, we call them longitudes, and then it means now the extraordinary, they will vibrate parallel to the lines of this longitude, but extraordinary. But now ordinary, they will vibrate parallel to the lines of latitude. All right. So yes, I hope you understand what we're trying to say. So let's repeat. We say the extraordinary rays will vibrate parallel to the lines of longitude, but now ordinary rays will vibrate parallel to the lines of latitude on this indicatrix. All right. So then extraordinary rays, when vibrate along radial lines symmetrical about the melatope, and then by so doing, the ordinary rays are in turn vibrating tangent to the secular isochrones. All right, they vibrate parallel to the tangent to the secular isochrones. So you see the light coming, converging from the auxiliary, and then passing through the sample, and then the sample must have the optic or optic axis that is vertical, the optic axis that is vertical, and then the light emerging from this center of this uniaxial indicatrix, like here. All right, and then what will happen is the extraordinary will be vibrating parallel to the lines of longitude, and then the ordinary will be parallel to the lines of the latitude, and then all of these things, they will be collected by what you call the objective lenses, and then now that's where we start to form the isogers. That's where we start to form the isogers. So let's see what exactly are these isogers. So isogers it's a curved or circular line or shape formed by points of equal interference figures. So if we have got points of equal interference figure interference colors, then would have what you call the isogers. So the isogers represent the locus point where the interference colors are the same at a given moment during rotation. Right, at a given moment during rotation. So the isogers become wider and have more diffuse edges further from the melatope. So they become wider and have more diffuse edges further from the melatope, or further from remember, melatope forms when the optic axis is parallel to the what we call the optic axis. So away from that, the isogers becomes wider and have more diffuse edges. So the isogers are formed where the vibration directions in the interference figures are north, south, and east, west. All right. Yes, you've seen that if they are north, south, and east, west, some of these vibrations, they will be parallel to either to longitudes, lines of longitudes, and parallel to the lines of, they will be vibrating parallel to the lines of latitudes. Hence, along these two lines, okay, condition for extinctions are obtained. That's where you see that a curved or circular line. Okay, yes. Now the mineral is dark along these two lines. It becomes extinct. Therefore, the darkness fades out progressively on the two sides of each line. So that's how the isogears they come into picture. So let's repeat for one last moment. So the isogears are just circular lines or the curved lines which they represent points of equal interference colors. So they represent the points of equal interference figures, and then these they are formed when the vibration directions of light in the interference figures are north, south, and east, west. All right, and then along these two lines, the extinctions start to come into picture. So the mineral now is dark along these two lines, and then we form what you call the isogears. All right, so I hope you understand. So the isogears here, you can now see them. That's what we call the isogears. These are what you call the isogears, wherein we see the conditions for extinction. We see the conditions for extinction there. They are 10 black, and then they represent the points at the points where we have the equal interference colors. So these are what you call the isogears. So yes, so this brings us to the end of today's session. That is, we're dealing with the interference figures, and these interference figures, they help us to determine the optic sign of uniaxial and biaxial minerals, and they also help us to know as to whether we are dealing with uniaxial or biaxial minerals. All right, so the next session will be dealing with the types of the types of interference figures or the interference figures in uniaxial minerals and the interference figures in biaxial minerals. Thank you.